Hello everyone and welcome to our channel, MooTechie. It's so wonderful to have you here as we dive into a fascinating and fundamental concept in chemistry and biology, the Nernst equation, and the factors that affect redox potential. Get ready to unlock how electrical energy and chemical reactions are deeply connected. The core equation we'll explore is E equals E degree minus the quantity RT over NF times the natural log of Q. This powerful formula is all about relating a system's reduction potential to its standard potential, temperature, and the reaction quotient. We'll see its importance not just in chemistry fundamentals and electrochemistry, but also in exciting biological applications. Coming up, we'll discuss the fundamentals. Fundamentals. What is the Nernst equation? It's a cornerstone of electrochemistry. Under the heading Fundamental Relation, we see the equation again. E equals E degree minus RT over NF times the natural log of Q. This equation beautifully relates the measured potential of a cell to the actual conditions it's under. It allows us to calculate an electrode potential under non-standard concentration, pressure, or temperature. And it has a solid thermodynamic origin, being directly derived from the free energy relation where delta G equals negative NFE. Next, we explore the general form. This slide is titled The Nernst Equation and presents the universal formula. E equals E degree minus RT over NF times the natural log of Q. It has several key features. It's temperature flexible, meaning it's valid at any absolute temperature T, which must be measured in Kelvin. It's activity-based. The quotient Q formally uses activities, but for our purposes in dilute solutions, we can approximate them with concentrations. And it provides a standard reference, where the potential EH is always measured versus the standard hydrogen electrode, or SHE. As we continue, let's understand the components. This slide breaks down the meaning of each term in the equation. First is E, the electrode potential. This is the actual potential difference of the cell or half cell under specific non-standard conditions, and it's measured in volts. Next is N, which represents the moles of electrons transferred in the balanced redox reaction. It's a unitless integer. Then we have E degree, the standard potential. This is our reference point, the potential measured under standard conditions of 1 molar concentration, 1 atmosphere pressure, and 25 degrees Celsius. The term RT over F is called the thermal voltage factor. This determines how sensitive the potential is to changes in the reaction quotient. A very useful note is that at 25 degrees Celsius, RT over F equals 0.0257 volts. For the constants, R, the gas constant, is 8.314 joules per mole per Kelvin. T is temperature and Kelvin, and F, the Faraday constant, is 96,485 coulombs per mole. Finally, there's a note on the scaling factor. The term RT over NF acts as a scaling factor, converting the chemical driving force from a concentration difference into an electrical potential, or voltage. And importantly, as temperature increases, this factor grows, making the potential more sensitive to concentration changes. Moving forward, we'll see some simplified forms. This slide shows us the equation at 25 degrees Celsius, or 298 Kelvin. We have two common versions. The natural log form is E equals E degree minus 0.0257 over N times the natural log of Q. The coefficients here come from substituting the known values for R, T, and F into the RT over F term. The more commonly used common log form, which uses base 10 logarithms, is E equals E degree minus 0.0592 over N times the log of Q. This base 10 form is the one most often used for quick, manual calculations because of its convenience. Now let's look at how concentration affects the potential. This slide asks how concentration affects EH. It explains the reaction quotient, or Q, impact. The ratio of products to reactants is what determines the potential shift. When Q increases, meaning products increase, the potential E decreases. Conversely, when Q decreases, meaning reactants increase, the potential E increases. There's an example given for a metal reduction reaction. M2 plus Z electrons yields M solid. For this simple case, the equation simplifies to E equals E degree plus RT over NF times the natural log of the concentration of M2+. Notice the sign changes to a plus when we take the log of the reactant directly. The key rule here is that a higher concentration of the oxidized species raises the reduction potential. The slide includes a simple diagram to visualize this. On the side labeled low concentration of M+, we have low E or low potential. On the side labeled high concentration of M+, we have high E or high potential. Now let's explore how temperature plays a role. This slide covers how temperature affects EH. The key point is that temperature scales the RT over NF term. The Nernst equation is directly proportional to temperature. As temperature increases, this thermal voltage factor, RT over F, grows linearly. This leads to amplified sensitivity. At higher temperatures, the effect of the concentration ratio is amplified, so small changes in concentration cause larger voltage shifts. The direction of change in E with temperature depends on the sign of the natural log of Q. This means the temperature effect can either increase or decrease the potential relative to the standard value. A table of thermal voltage constants shows how RT over F changes with temperature. For example, at 0 degrees Celsius, it's 23 millivolts, at the standard 25 degrees Celsius, it's 25.7 millivolts, and at a physiological 37 degrees Celsius, it's 26.7 millivolts, with values for other temperatures like 100 degrees Celsius also shown. This slide highlights practical applications in chemistry. The Nernst equation is a fundamental tool that enables precise calculations in many areas. We can calculate cell potential to determine the exact potential under any non-standard condition. We can find equilibrium constants like K or the solubility product KSP by measuring the cell potential when the system is at equilibrium and E equals 0. It helps us analyze concentration cells, which have identical electrodes but different ion concentrations, to predict the direction of electron flow, which is always from the low concentration half cell to the high concentration one. And it's the core operating principle behind pH measurement in pH meters, where the potential difference from a glass electrode depends directly on the hydrogen ion concentration. Following this, we'll discover its incredible applications in biology. This slide delves into applications in biology where the Nernst equation is crucial for understanding life itself. It's used to calculate ion equilibrium potentials, which is the potential where an ion's electrical drive balances its concentration drive across a membrane using the formula E ion equals RT over ZF times the natural log of the concentration outside over the concentration inside. For membrane voltage, the more complex Goldman-Hodgkin-Katz equation extends the Nernst principles to calculate the membrane potential when it's permeable to multiple ions like sodium, potassium, and chloride. In physiology and neuroscience, specialized forms of the equation at body temperature are used to predict resting potentials and the thresholds for action potentials in our neurons. And it's used to understand metabolic redox couples, determining the cellular redox state and the free energy available from vital reactions, like the NAD+/NADH couple in cellular respiration. Finally, let's wrap up with a summary. This summary slide gives us the key takeaways. We revisit the core relationship. E equals E degree minus RT over NF times the natural log of Q, and its simplified form at 25 degrees Celsius, E equals E degree minus 0.059 over N times the log of Q. This provides a fundamental link between thermodynamics and cell potential. The primary drivers are concentration through Q and temperature. Higher temperature increases the system's sensitivity to concentration changes. We should remember the distinction between precision versus approximation. The equation formally uses ion activities, but concentrations are a valid approximation in dilute solutions. And we've seen its broad utility, being essential for everything from battery efficiency and pH sensors to equilibrium constants and the very membrane potentials that allow our nerves to function. Thank you. See you in the next class.